So I believe where we ended was looking at Bohr's model, or Bohr's addition to the model of the atom. Our electrons now exist in these orbits around atoms. And we said that we had the evidence for this because we looked at, say, hydrogen as a gas. The electron's as close to the nucleus as possible, the lowest energy state. We put in 20,000 volts. That causes the electron. So here's our cattle prod. Causes the electron to jump up. So we've provided enough energy to cause the electron to move to a different state. It's now super excited. See, there's the air particles because it's excited, right? They show that in the cartoons. Right? It's now excited. Right? Doesn't want to stay excited. Right? Just like you guys. You had to walk to get here. That's a higher energy state. And then you came in here and you sat down. Right? You don't want to stay in that excited, constantly moving state. You want to relax. So you want to relax back down. Right? In the process of coming back down, though, the energy has changed. Right? And one of the things that Einstein tells us, and we'll go back and talk about Einstein later, is that you can't create or destroy energy. Okay? You can convert it from one form or another, but you can't get rid of it. So the electron at that higher energy state has more motion. Right? When it drops to the lower energy state, it now has less motion. So we've lost some energy there. Well, that energy has to go somewhere. Where that goes, in the case of most of our elements, in these kind of configurations, is light. The excess energy comes back out as light. That is visible light that we then see. So if we looked at, if we backtrack here, hydrogen, we saw 3 lines. Okay? The details of those 3 lines is not what we're about to show, but it's going to get close enough for approximative sake. So we had the violet, we had the blue, and we had the red. Okay? And I need to add another orbital, so here's another orbital. Okay? If I jump from that outermost orbital all the way down to the innermost, okay, that is one possible transition. 20,000 volts is enough to get the electron from that initial state outside the entire atom itself. Okay? So that's one transition. Here's another transition. And here's another transition. So there's 3 possible transitions for the structures I've got shown. Okay? Why did I pick this structure? Because we had 3 possible colors. We had red, we had violet, and we had blue-ish. Which of those lines is red? Okay, the shortest one. Red had the lowest energy, so that's going to correspond to the shortest gap. The violet has the highest energy, so that's going to correspond to the largest gap. Trust me, that's now purple. And then blue is now that intermediate one. Okay? To a first approximation, that's what is happening within our atoms. Okay? So it's the observation of the atomic line spectrum that tells us that the electrons can't exist anywhere. They must exist at these steps, at these orbitals. Okay? This is the concept of quantization. They're quanta. Boosh. They are quantized. There we go. Let's try that. Okay. Really all we're saying in that is that we have steps, not a continuous line. A rainbow does not have steps. It's not red, then orange, then yellow, then green, then blue, then indigo, then violet. It's red that slowly, gradually becomes orange, that slowly, gradually becomes yellow. Okay? This ramp is an example of the rainbow. Okay? The stairs are an example of our electron orbits, where they can exist. Kind of make sense? At least enough that you should just accept. Let's try that. Okay? So if we actually scaffold this out a little bit further, our diagram now shows 7 orbits Orbit 1, 2, 3, 4, 5, 6, 7. Okay? There are 7 orbits for all elements on the periodic table. Okay? Sort of. There are 7 energy levels. Okay? And that's what's really happening when we're seeing the atomic line spectrum. We're seeing our electrons jump between different energy levels. Okay? Well, remember I said that our final organization for the periodic table had to do with Bohr's development or theorization of the energy levels, okay, of our electrons. So those 7 energy levels had better show up in the periodic table. Where do they show up? Groups. Group was what? Vertical or horizontal? Vertical. How many groups do you see across the periodic table?
18.
Okay, 18. So not 7. Not a bad idea, but didn't work. Well, they aren't groups. Columns are groups. That's the vertical part. It's okay. Maybe it's the rows or our periods or our series. Okay.
I don't know what it is, but it's just like the 2 on the side, the ones that aren't all the way up, the transition metals, and then the big block on the right.
Okay. So you're seeing that we have 2, a section in between. So you're actually taking this periodic table that looks like a giant lump and saying there's lumps that actually look like they're grouped near each other. So how many groupings of lumps do you see on the periodic table?
5.
You see 5?
There's 2 on the top that are
Let's see.
cells.
1. Okay, I see what you're doing. You're taking that as a group.
Or just hydrogen and helium are their own.
Okay, I can accept that. So the hydrogen and the helium, not a bad idea to actually separate those out entirely from the periodic table because their chemistry just gets weird. Okay, so one group being hydrogen and helium, the second group being the first 2 columns, another group being those middle 10, another group being the last 6, so we're up to 4, right? And then another group being this bottom one, that would be 5. Okay. I like your grouping. That is incredibly important. Unfortunately, it doesn't match this. Okay, so that will come back, but not yet. There are 7 energy levels. Even if we look at the groups at best get us 5, not 7. So where are the 7 coming from? The periods, which would be the horizontal rows on our periodic table. So how many periods do you see on the periodic table?
7.
So hydrogen, lithium, sodium, potassium, rubidium, cesium, francium. But then don't you see lanthanum and actinium?
Those go up there though? They just
Okay. Where do the lanthanum and actinium series go? They're officially embedded in the periodic table above. Why did we pull them out separate? If we'd put them in where they actually belong, our periodic table now isn't a somewhat sort of nice squarish looking thing. It's now a massively long rectangle. Right? So we've decided to pull those out as separate to kind of condense the periodic table down to make it a little bit easier to work with. Okay? Why else can we get away with that? Okay? All of those elements, or a significant number of those elements, are man-made. Okay? They're all synthetic. Okay? Well, sorry, say that again?
Is it the white one?
Yep, the ones that are outlined are synthetically prepared. Okay? So most of those we just made up. And they aren't relevant is a bad word to say, but they aren't relevant because you will never work with them. Okay? The ones above that do exist on their own. The ones in black do exist on their own, okay? But their masses are really, really high. And what did we say about masses that were really, really high? Anybody remember? We had atomic notation. I said atomic notation is a bad way to call it. We shouldn't actually call it atomic notation. We should call it nuclear notation because it's in reference to the nucleus. Who uses nuclear notation? Nuclear engineers, nuclear chemists, nuclear physicists. What are they studying? Radioactivity. Virtually everything in that bottom two sections are radioactive. How many of you are ever going to work with those radioactive elements? Okay, probably none of you ever. Okay, so we can pull those out as a secondary level and not worry about them quite as much because you just aren't going to deal with them. So why make our periodic table look unwieldy or more unwieldy by inserting them to make them look equal? We'll just pull them out because we'll rarely deal with them anyway. Okay? This condenses our periodic table and looks a little bit cleaner. So our 7 rows are indeed 7. Okay? The lanthanums, La and actinium, whatever it is, La and Ac are inserted into it. There are 7 rows. There are 7 rows because there are 7 energy levels. Okay? So the structure of the periodic table has this information embedded in it. When I went through and drew out and said what the colors were, I had those 3 arrows. Notice we have 3 arrows drawn on this. I've already drawn red, purple, and green, or blue-green, whatever you want to call it. But my arrow ended at 1. Where do these end? At 2. Why are they ending at 2 and not at 1? What if they ended at 1? What would happen? Okay. So let's say for the red one, let's say instead of going from 3 to 2, it went from 3 to 1. What happens to the energy? It increases. It becomes a larger energy because it's a longer arrow. Okay. Which then means, is it red? No. What color does it end up being? More closer towards the violet. That arrow now is actually longer than the violet arrow. Which means that transition does exist, but where is that transition happening? Outside of the visible range. We can't see it. Okay? So some of the transitions, all of those transitions are possible. Some of them happen to fall in the visible range because of the energy gap, matching the visible energy spectrum. The other transitions still happen, but they happen outside of the visible spectrum, so we don't see them. Right? So the atomic line spectrum just happened to be whichever transitions happen to fit within that tiny little band that is the visible spectrum. Okay? So for the case of hydrogen, I think it actually has a name. It might be the Balmer series or something like that. I don't know. We're talking about the transitions from 3 to 2, 4 to 2, and 5 to 2. Those are the transitions that generate the color of our atomic line spectrum. Okay? You don't need to memorize those numerical values. You need to understand why those values are there and what it means. What it means, we have orbits. That's it. We have orbits. The electrons have to be in that particular energy level. They can't be in weird gray areas in between. Okay? What can we do with these? Okay, well, if we go through and take a look at a continuous spectrum, there's our rainbow. If we go through and look at helium, how many lines do you see for helium? 6. Some people, should it be 7? 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 lines there. Some of them are hard to pick out because of their proximity to each other. But if we looked at helium, we see 8 lines. What happens when we move to lithium? You see 4. Sodium, 2. Mercury, a different amount. Okay? So the number of lines changes as we change the element. Not only that, but do we see the exact same colors show up in each of those? No. Well, why not? When we move to a different element, what has changed? What changes when we go from hydrogen to helium? Different mass, so we're really saying a different amount of protons. Those protons are holding on to the electrons. The electrons exist in orbits, but those orbits are defined based off of the interaction between the nucleus and the electron. If I change the nucleus, does that change the orbit? Yes. So every element has a different atomic line spectrum because every element has a slightly different energy level for each of their orbits because they have a different nucleus and they have a different amount of electrons. All of those things add together to result in different atomic line spectrum. That in and of itself doesn't seem like a big deal, but if I was going to try and identify somebody or hide from the world, I might try and make myself look similar to somebody else. Right? So I could change my hair, change my face, get surgery on my face or something like that. Okay? So that I could look like one of you and then I could dissolve into the crowd. Okay? Or blame you for anything that I went out and did, like rob a bank. Now it's your fault that you robbed a bank. Okay? Except what's one of the harder things for me to go through and change? My fingerprint. My fingerprint is going to stick with me. Okay? I can get surgery to change it, but then eventually what happens? My skin falls off and my original fingerprint grows back. Okay? The fingerprint sticks with us. Same thing with our atomic line spectrum. We can use the atomic line spectrum to identify our elements. We use this in astronomy because we can aim a telescope out there and look at the atomic line spectrum of the light coming back at us to tell us that this element is in that star. This star has more of that element because we can decompose the light that comes back into the atomic line spectra. Okay? When we look from a star, we're not seeing pure helium. We're probably seeing a mixture. So what we would have to do is kind of separate that information out to see which ones matched the overall image. So it's a pretty neat process. We can look at the atomic line spectrum to identify an element. Okay? So let's take this to our electron homes. How many energy levels did we say existed? 7. So we could add our 7. Okay? And if I did this right, which I never do, let's start with 7 up at the top. Not quite 7 at the top. We'll go 7, 6, 5, 4, 3, 2, and 1. Okay? Notice that the distance between each of those orbitals is not the same. Okay? It gets increasingly tighter and tighter, or increasingly closer to each other. Why would that be the case? Okay, well, I didn't label the very top one. What happens when I get to that very top one? What is that line? Okay, we're effectively talking about the pen that I'm holding here and moving that pen further and further from me. Eventually, what happens when it gets far enough out? I break the connection with the pen. Okay? That pen is my electron. The further the pen gets away from me, eventually I can't hold on to it anymore and it's gone. For an atom, what we're saying is that means the electron has now moved so far away from the atom, it is no longer attached to the atom. Well, then what is it attached to? Okay. Well, in our simplest picture, all we're looking at is a single atom. So what is outside a single atom if all I have is a single atom? Nothing. What's another name for nothing? Space. What's another name for space? We needed it to discover an electron. Good. If you're all getting that wrong, I'll add that as a test question. We needed a vacuum. Okay, which I can't spell. So the highest energy is really the vacuum. Once we've hit that, we're no longer associated with the element. Okay, which is why as we move up, I can't continue to space them equally, because if I space them equally, I would be beyond the vacuum. Okay? There's a max energy. Okay? And our elements, our number one, is going to get as close to the nucleus as possible. Okay? Which then shields the other ones and making them having to go progressively kind of further away from each other outwards. So we can't evenly space all the way through. So we get this odd kind of stacking out of this. Okay, kind of makes sense? The nucleus, for the sake of argument, okay, is not at the bottom of the page, because then that says those are really close. Okay? The nucleus is probably down here. Okay? For those of you who can't see me, I'm pointing at the ground. Okay? So, 7 energy levels. These are where my electrons exist. So the first electron, I would expect to go into that first energy level. So there's my first electron. Ta-da! Where would I expect to put the second? What's that?
The second one?
Why would I put it in the second one and not the first one?
Because they only have one.
Why can it only have one electron? Electrons repel. Okay? Similar charges repel. So it makes sense that the next electron has to go in the next highest energy level, right? Okay? So we use that as our theory. How many electrons would I be able to put in any atom? 7. Is that what our periodic table tells us? No. So our theory is bogus. We're missing something. It turns out one of the things that we're missing is that electrons have a spin state associated with them. Okay? That spin state, there's really 2 possibilities. And it's not even really a spin state, it's a phase. So we'll try that argument. What do you mean a phase, Mike? Okay? It's a wave. Electrons have a wave particle duality associated with them. Don't stress too much on this, which means they can move something like this. Okay? If I'm over here, the spin state ends up being positive. If I'm over here, the spin state is negative. How did you come up with that? What am I drawing in purple? The axes. Okay? The positive one has the existence of the electron in the positive quadrant of our axis system. The negative one has it in the negative axis of our system. Okay? Which means for every orbital, I can place in 2 electrons. One in the positive state, one in the negative state. Okay? The other way that that is described, because a lot of people have a problem with these whole probabilities and phases and all that, I don't blame you, is that we just say electrons have 2 states. Okay, or 2 possible spins. They can spin up, there's an arrow up. They can spin down, there's an arrow down. Which means every orbital can now hold 2 electrons. Okay? Because one of those electrons is spinning up, one is spinning down. Cool, so it's not 7 now. How many would I get? 14. So that's better. That's now accounted for. Does that account for my periodic table? No, because according to my periodic table, I can get up to 118. And I'm at 14. So my theory is still flawed. Right? The next part of this is that we find that we have to have sublevels. Right? That every time we move up in energy, we duplicate what we had before, but we can add another type, okay? Another sublevel. So when we start at the first energy, we only end up with one type. That one type happens to look like a sphere. Okay? It's a circle. When I move up to the second energy level, I get 2 types. Okay? So it kind of splits. I would get a repeat of what I had before. Okay? It's not identical. In fact, I can fix that. Because that repeat is at the second energy level, not the first. It's still going to look like a circle, but it's going to look like bigger circle because it's at a higher energy level. Okay? And I add a new type. Okay? So every time I move up, I can add a new type. So the new type that I add looks something like this. Okay? It can't look like a sphere because the sphere has already been taken. Okay? That means that I can now, just getting to the second energy level, account for 6 electrons, right? 2, 4, 6. Yeah? Add in the third energy level. I'd get a copy, 2, another 4, and because I'm now at the third energy level, I'd have another type, another 6. I could go through and do that now for every single one of my energy levels. That adds a significant amount more of electrons, yeah? Does it add to 118? No. So what happens is we start with our energy level, it didn't account for it. Okay? So we had to manipulate and deal with the mathematics in our calculations to hopefully find an answer. Okay? And so we dug deeper into it and find that we didn't account for sublevels, okay? Which is ultimately a type of orbital. Okay? That still didn't account for it, so we dig deeper and we now find that we also have what's known as an orientation of each of those sublevels. Okay, so let's start all the way down at the bottom with our one energy level sphere. If I take a sphere and change the orientation, would you be able to tell that the orientation has changed? No. Why not? It's a sphere. It's completely perfectly symmetrical. I'd never be able to tell that it changed, which means how many orientations are possible for that sphere-type orbital? 1. Okay. There's a lot of ways you can spin it, but you wouldn't be able to tell a difference between them. So it ends up coming out as 1 possible orientation. Okay. How about for the next orientation? Okay. So I could take that, and if I change the orientation, could you tell that I changed it? Yes. So you're telling me 2, because I got up and I have sideways, right? Remember, molecules are 3-dimensional. All you've told me is 2 dimensions. Okay. There's a third dimension. We can align that orbital on the x, y, and z axes, which means there's now 3 orientations for that. Okay. That last one is coming in and out of the plane at you. There's nothing I can do to draw that except pretend that that's what that looks like. So we just agree that I did a good job. Okay. When we move up to the third energy level, well, I'd get a repeat of the sphere. I'd get a repeat of the dumbbell shape, all 3 of them, and now I would add yet another orientation, or another type. That type I can't draw. Oh, that's a lie. I can draw that one. That next one looks something like this. Okay. And it turns out that that one has a whole bunch of orientations associated with it. Okay? So let's take a minute and breathe and kind of absorb this. Let's start with the first one. I want to now start placing electrons in. How many electrons can fit in the first energy level? 2. I can always fit 2 into a single orbital. Because that first energy level only has the sphere, there's no different orientations. I can only place 2 electrons in. When I move up to now trying to put in a third electron, I can't place it in the first energy level anymore because there's no more space. So I move to the second energy level. And I'm going to place it in the sphere first because it's lower in energy than the dumbbell shape. Okay? So how many electrons can I place into that? 2. And again, because there's only one orientation for the sphere, there's only that one shape. I'm done. Okay? So there's 2, 4. Where does the 5th go? Into one of the dumbbells. So there's the 5th one. Where does the 6th go? Okay? Into our dumbbell again. Which dumbbell now? Because I've got 3 dumbbells. Okay? So there's this thought, well, we have to fill before we move up, right? That's true. You do have to fill before you move up in energy. However, is the next dumbbell the same energy or a higher energy? It's the same energy because it's still the same orientation in the same energy level. Should I be pairing before I move up? I can place in the next one over. Why place in the next one over and not here? If I pair them, I now get the electrons near each other. Yes, the opposite spins means I can fit 2 there, but that doesn't mean I want to fit 2 there. You have 2 cars and 2 like normal size cars, small cars-ish cars, and 5 people. Okay? A small car can fit 5 people in it. Do you try and cram all 5 people in? Okay? Depending on your costs, mode of transportation, and all that, you could factor all that in. But whoever gets the middle seat in the back, probably not going to be too happy about it, and it's going to say, let's take 2 cars. Okay? Yes, it works, but if we have the option, we'll do it. Same thing's happening here. Okay? I have an option, I'm going to do it. Where's the next electron go? The 3rd one. Where's the next electron go? Right. And now any one of those, because they're now all equivalent. It doesn't really matter which one, so we can put it in the first one. The next electron. Next. And the next electron. Now I have to move up to the 3rd energy level, and I'd have a sphere. I'd have my dumbbells. I'm not drawing all the dumbbells again. Actually, I'm not going to draw any of those shapes. We'll just draw a line. There's 3 of those. And then there's 1, 2, 3, 4. Never mind. Let's ignore that for a moment. Okay? And I can now start adding electrons into each of those. Okay? And then I could go up to the next orientation. Kind of, sort of? Okay.
Are we going to get tested on, like, how deep in will we get tested on this?
All sorts of different levels on this. We'll talk about it.
Okay.
Okay. This kind of drawing you're not expected to do again.
Okay.
What this drawing does is help to organize and make it look pretty and provide the logic behind why it's there. Okay. What you will find is what you get tested on is we remove all of the logic and just want the answer. Okay? So if you understand the logic behind it or you've memorized the process, you're okay either direction. Okay? So now what I want to do that we've gotten to a sizable amount through here is say, does our periodic table take advantage of this? Okay, well, we said the 7 energy levels corresponded to our 7 rows. Okay, so in our first energy level, how many elements are present? So our first energy level is that very first row. I've got hydrogen on the far left, and I've got helium on the far right. Yes. Okay. Which means 2. How many electrons could I fit in the first energy level? Ooh, interesting. I could fit 2. When I move to the second energy level, how many elements do I have? I now have 8. So let's move to our second energy level. What do we have? 1, 2, 3, 4, 5, 6, 7, 8. Interesting. Okay. the organization of our table allows us to manipulate and see this. Okay? Add to this. Okay? Remember the hydrogen and the helium are a weird one, so we're just going to deal with our second energy level. We start with lithium. The very first electron in the second energy level went where? Into the weird sphere shape, right? Where'd the second electron go? The sphere shape. Where'd the third electron go? Into a dumbbell. So a different shape, right? Might be nice if there was kind of like a gap on the periodic table to say, hey, those went into the sphere shape, these went into a different one. You following me? That's lithium, beryllium, right next to each other, in the same shape, followed by a massive gap, because we're now moving into a different shape. All the elements in those first two columns, their outermost electrons go into the sphere shape. Everything between boron and neon, their outermost electrons go into the dumbbell shape. How many electrons fit in the dumbbell shapes? 6. How many columns are there? 6. That information is stashed within it. So we can sometimes refer to those first two columns, instead of calling them alkali metals and our alkaline earth, we can call those first two columns the S block. Crap, I didn't say that yet. Spheres. We can call it the sphere block. Okay? The boron to neon section of the periodic table we can call the dumbbell block. Okay? When we moved up to that third, right? We add a new level. Okay? That information needs to get stashed in here. And I started to draw in a bunch of lines for where those orientations were. Okay? We know the S block has one orientation because there's two columns. Wait, how does 1 equal 2? 2 electrons go into that single orientation. We know the dumbbell has 3 orientations because I have 6 columns. How does 6 equal 3? 2 electrons in each. Okay? If I move left to right through this, what's the next new section I encounter? What element? Okay. RSC. Okay. Ti isn't part of the S block, isn't part of the P block. If I continue to move through, zinc is the last one in that column or in that sequence that isn't already in the P block or the S block. Because as soon as I move to the sphere or the dumbbell, as soon as I move to gallium, I'm now back in the dumbbell block. So between zinc and scandium, I have a new type, a new block. How many columns are there in that block? 10. How many orientations are possible for that block? 5. Because each of those 5 can hold 2 electrons. 2, 4, 6, 8, 10. There are now 10 orientations for that next new type. Okay? Here being the clover leaf. When we move to the next one, the 4th energy level, what's going to happen? I'm going to get another new type. Okay? Where's the new section on the periodic table that we haven't addressed yet? The bottom 2. The bottom 2 rows, okay, are their own separate section. How many columns are in that? 14. How many orientations are there for that new type? 7. Okay. All of the electron configuration stuff is stashed in the periodic table. Okay. You have to be able to read the periodic table to find that information. It's buried in there. That's part of this practice in the course. Okay? I already started to allude to some different kind of terms that came out of this. Okay? For instance, well, actually not for instance yet. We called that bottom one the sphere, because it looks like a sphere. Okay. That weird loby one, we called a dumbbell. What about the red one? We'll call that a clover leaf. Okay. Probably the only one that actually makes sense to anybody is the sphere, and everything else you're like, you're just making that up. Yes, we are. Okay. But you're responsible for knowing that we made that up. Okay. Do we really want to call those first two columns the sphere block? It's not all that hard. Dumbbell block, cloverleaf block. Okay. Scientists are inherently lazy. That is way too many letters. That is way too much stuff to write out every single time. I want to come up with an abbreviation for that. What would be a good abbreviation for sphere? S, because sphere begins with S. I like that. Okay. What would be a good abbreviation for the dumbbell? D would make a lot of sense, right? Because dumbbell begins with D. But we'd be wrong. We call that P. Cloverleaf, what would our symbol be? Okay. We might go with C. No, it's our D. Okay. And for those of you going, but cloverleaf does not begin with D. I'm aware of that. Okay. But also please be aware that a lot of these kind of symbols used to describe these did not necessarily originate from the English language. Okay. What was that?
We need more American elements.
Just because you mentioned that. You need more American elements? What's 95?
American?
Yeah, pretty much.
Cool.
We get real fancy in the pronunciation to make it sound less like we were just being selfish. Americium. But if you write that out, that's Americanism, effectively. I thought it was CF. Yeah, CF. Californium. BK. Berkeleyum. Okay. So there's plenty of stuff on there that's American. Okay. So that was a slight sidetrack. So what we've got now is a labeling system, because I can go through and now tell where any electron is located. I can pick an element and say these are where the electrons are located for that element. Okay? So I could go through and draw out a diagram like this every single time I wanted to describe that. Okay? That's a lot of stuff to draw. In fact, it didn't look like very many of you drew it. Okay? Thank you. I went to all that work, and you didn't even respect that I did that work. Okay? You're not even taking pictures of it. Jeez, this is horrible. Go ahead.
So, like, all these, like, man-made ones, you said it takes billions just to study and make these things, usually. Do we ever use, do we ever use these? Or
Well, we know.
Not, like, us personally, but does anyone really use it?
Yeah, somebody had to make them.
What's he use them for?
To be able to attach a name to them. It's largely what it is. Yeah. That's about it.
No, okay.
Okay. We're trying to get more information about it because we want to learn more about the nucleus and its atomic structure. What makes things have mass. So that's where you can bring in the Hadron Collider and all those other kind of things. Is we are trying to find information about that. That information hasn't trickled its way down enough to us to be able to use anything with. Okay? It would also be well above what we want to deal with at this point. Okay? So I want to look at hydrogen. And I don't want to erase all the electrons, so I'm going to look at hydrogen. I'll draw it in red. So hydrogen, I want to know where hydrogen's electron is. Well, how many electrons does hydrogen have? One. So if I've got this drawing, I could say, well, that one electron is going to go right here. There's my one electron in red at the bottom, right? So I'll place it the lowest energy first, because we're lazy. We won't sit down. Okay, or bow, curtsy, whatever that was. Okay, so we want to place it there. Okay. But I don't want to draw all that. So how could I describe that one electron went there? Where is there? It is an S. Okay? I agree with that. Okay? But which S is it? because there's this one. Did it go into that S? No. So what's the difference between the blue S and the black S? And don't tell me blue and black. The energy level. Okay, well, what did we name the energy levels? 1, 2, 3. We're creative. Okay, so that first energy level is 1. So that configuration up there, I need to specify the energy level for where the electron was located, and then the orbital I placed it into. So that would be the 1s. Well, how many electrons did I place into that 1s orbital? 1. So I'll call it 1s1. I have now done electron configurations. Woohoo! Okay. So as you're going, that was too easy. Yeah, I know. Let's make it helium. Okay, how many electrons does helium have? 2 electrons. So the first electron goes where? First energy, 1, S, almost, 1. Where's the second electron go? 1, S, 1. Right? That's kind of repetitious, right? Is there a way we could condense that? Say yes. 1s, 2. I've now done the electron configuration for helium. Make sense? You got it? Think you could do it on your own? Let's switch to purple. Okay. Give me the electron configuration for iridium. I changed my mind. Let's not do iridium. I just wanted to see how many people would panic before they found it. Let's try phosphorus. Phosphorus is a little more reasonable. Let's try phosphorus. We have my lovely drawing. In theory, you can see the colors there now in purple. Put them in 2, 4, 6, 8, 10, 12, 13, 14, 15. So in purple on my drawing, we've got all the electrons placed. How many electrons did I put into the 1s energy level? How many electrons did I put into the 2s energy level? How many did I put into the 2p?
6.
How many did I put into the 3s?
2.
How many did I put into the 3p? There's my electron configuration. Drawing is nice, right? I just put them in and there it is. Okay? So what you're responsible for doing is what is the electron configuration for phosphorus? That's it. You have to be able to draw that out. What if you don't have this nice pretty drawing? Whoops. That was a bit unfortunate. Why would you go through and delete that, Mike? Were you about to take a picture? Okay, go ahead and take a picture. Okay. What happens if you don't have all of that nice drawn out already for you? Well, it would be nice if you had a way to look at the organization of our periodic table. Do we all get our pictures if we wanted them? Okay. So let's go back and look at our phosphorus. See where phosphorus is located, right? Column 15, row 3. Okay? It's in the P block. Right? Which column of the P block? It's the third column of the P block. Okay, so I've got P3. Which row? Okay. That's right. Everybody see that? Okay. What has to happen with everything before it? Those things need to be filled. Okay? So since I memorized that it goes 1s, 2s, 2p, 3s, I now need to go back through and just fill those. Well, the s can hold 2 electrons. The s can hold The P can hold. The S can hold 2. There's my electron configuration. Okay. So I can jump to the end, use the coordinate system of the periodic table to tell me what that last orbital is, and then just backfill everything else. Okay. Some people are okay with that, some people aren't. The part that usually trips people up is that would mean you'd have to know the sequence. Yes. Yes, you do. Any way you slice it, you have to know the sequence. Okay? You have to know how those things fill. Okay? The periodic table does give you that. We start at 1. How many electrons can I fit into the 1? 2. The first shape I start with is the S, so it has to be 1s2. Second row, I have 2 all by themselves, so that's going to be 2s. 2s, at most 2. The next block, second row, I hit 2. There's 6 columns in that block, which means at most I can fit 6 electrons. That's which block? The P block, 2p6. Okay? The information is there, you just have to be able to do that interpretation, and it takes practice. Open up pretty much any textbook, and you should find that they list out the electron configurations for every single element. If it's not in your textbook, just Google electron configurations. They will give them to you for every single element. You now have 118 practice questions.
Do you have to write it that way, or can you write it?
So this way works. Most people seem to be happy with this. Every time I go through and show the abbreviated way, I usually lose about half the class. Okay. So it is entirely up to you if you want to abbreviate this notation or not. The abbreviation only comes into play with the noble gases. So we could go through and say the closest noble gas to phosphorus that I've passed through in the process of filling the electrons is neon. I haven't reached argon yet, right? So what is the electron configuration for neon? Well, neon has 2, 4, 10 electrons. So those first set right there, I could just say as well, it's the electron configuration for neon plus 3s2, 3p6. That's a shorthand. That is perfectly valid. Okay, but again, that tends to confuse a lot of people. I'll stick with the longhand when it comes to the exam. As a show your work, this is not a show your work question. Okay, it's straight multiple choice. Okay? So, questions that could get asked out of this, what's the electron configuration for X element? Not for X element doesn't exist, but an element I give you. Okay? The elements that I will choose will probably be within the first 3 rows. Why would I pick those? Because it gets a lot more complicated as you drop lower and lower. Okay? Remember, the reason we move up to a new orbital type is because we filled everything below. Well, there's exceptions to that. The exception has to do when our energy levels get so close to each other that now another thing comes into play. Well, what's that other thing? Symmetry. Symmetry. Why would symmetry have anything to do with it? If you close your eyes, work with me, because I don't want you staring at me. You'll understand. Okay? Yes. That means close them. Or at least not look at me. That's fine. Now, as people are now staring me in the eyes, okay. Imagine the most attractive person that you're aware of. Okay? If you slice away half of their face and mirror the remaining half across, it looks the same person. Okay? You can open them again, but that's the whole, I didn't want you staring at me for that. Okay? Studies have proven this to be true. The people that we find most attractive as a population are symmetric. The less symmetric a person is, the less attractive they appeal to the larger population. Okay? Kind of a bizarre system, but chemistry does the same thing. And what ends up happening particularly as we move between 3p. So after 3p, what would we expect to fill? Okay. We're at the third energy level. We would expect to fill the next orbital type, right? Which would be the 3d. But what do we fill after 3p? Fourth energy level, I'm in the S block, not the D block. I fill 4s. Why did I skip 3d? Symmetry. Okay, if you want more information than that, feel free to talk to me about it. Okay? When you move into 151, if you move into 151, they'll go into it in hopefully a little bit more detail. They may not tell you symmetry. They may just tell you, the periodic table tells you your electron configuration. Okay? The other thing that can get asked, we'll ignore all that, okay, is everybody tends to freak out about, this is ultimately where the electrons live. That's it. It's an address, period. Don't treat it as anything more complex than that. If you want somebody to get to your house, you don't just say show up. You have to tell them an address. Okay? The address, the number of your house, the street that that number applies to, the city that that street applies to, okay? The state, okay? The country, the continent. Okay? All of that information is stashed in an address. The same thing is going back with our electron configurations. You're just identifying the location of every single electron for an individual atom. Okay? The next layer that gets added onto this for questions would be, what is the S-type orbital shape? Sphere, dumbbell, or cloverleaf? Sphere. Answer solved. Okay? So you're responsible for knowing what those shapes are and to what orbital type they apply to. Okay? You're also responsible for knowing how many orientations are there. How many orientations are there for the sphere? 1. How many orientations are there for the dumbbell? 3. How many orientations for the cloverleaf? 5. Okay? I wish there was something that had that information stashed for me so I didn't have to memorize that. How many orientations for the S? 1, because there are 2 columns, and I can fit 2 electrons into each. How many orientations for the P? 3, because there's 6 columns, and I can fit 2 electrons into each orientation. How many orientations for the D? Well, there's 10 columns. 2 electrons into each gets me 5 orientations. Okay? The periodic table has that information stashed in it. You again have to be able to interpret it. Okay? So you either learn to interpret or you learn to memorize. Either was fine. Okay? There's our orientations, so we can see those. Okay? Just because this one's fun, there's our D. We said there's 5 orientations for our D. Okay? So all that's happened is we've changed the coordinate plane that 4 lobes are located on. Okay? Oscillate, oscillate the 4 lobes, oscillate the 4 lobes. Anybody have an issue with that? Does that look like a cloverleaf? No. What happened? Quantum physics. That's what happened. What's this shape look like? Kind of a dumbbell, but not a dumbbell. What makes it different than a dumbbell? It has a donut around it. It's the dumbbell donut. Okay? That's the last orientation of the d orbital. Are you responsible for that? No, don't stress about it. You're more responsible for up here. Okay? So, orbital capacity for the first energy level, how many electrons fit in the sublevel? 2, because the s orbital can only hold 2. How many electrons in the energy level for 2? Or sorry, for the first energy level? 2. Okay. What happens? No, go away. I didn't do that. Thought I was going to show too much. The second energy level. How many energy sublevels are there? I have the 2s and I have the 2p. How many electrons fit in the s orbital? 2 electrons. How many electrons fit in a single 2p orbital. 2 electrons. How many 2p orbitals are there? 3. How many electrons fit into the 2p orbitals? 6. For those of you being like, that was really nuanced in words, yes, read your questions carefully. How many electrons fit into the second energy level? 8 electrons. Okay? So that's another level that can get asked out of this, is pausing at each and every single one of those stages to say how many electrons are there. How many electrons are there? How many electrons are there? Make sense? What happens if we move to the third energy level? Well, we'd get the 3s, the 3p, the 3d. How many electrons into the 3s? 2. Into the 3p, 6. 3d, 10. Total electrons in the third energy level? You just add them up, 18. You could do the same thing with the fourth energy level, technically the 5th, 6th, and 7th. Okay. Why do we not typically talk about the 5th, 6th, or 7th? We move up to the 5th, what are we going to repeat? S, P, D, F, and what do we have to do? Add a new type. Okay. What's that new type? We haven't gotten there. Okay. Turns out that we don't need to add a new type because of how the electrons fill. We satisfy all of our 118. Okay? Will we be able to find that new type eventually someday? Maybe. Okay? But we aren't there yet. Okay? We already talked about all that. You'll see reference sometimes to an electron filling diagram where you just layer them out. Notice it goes 1s, then 2s, right? We kind of weave through 2s, then we'd fill the 2p, right? We talked about it, then the 3s, and then we'd fill the 3p, that makes sense, 3p, then 4s. We'd be like, well, that's weird. Remember, the periodic table told us that already. Okay? 4s, we loop back through, we'd fill the 3d, followed then by the 4p. Periodic table tells us that, followed by 5s, loop back through, 4d, etc. That diagram, in theory, makes sense to some people. I can't write in straight lines, so mine makes no sense whenever I do it. Okay? If it's easier for you to use that electron configuration filly thing, great, do it. If it's not, don't worry about it. Okay? The periodic table covers most of that information already. Okay? The last thing we really want to get at, which is super, super important, because it applies to our chemical properties, is this valence electrons idea. Okay? When I looked at phosphorus, there were really 2 ways that we could have written out that electron configuration. 2s2, 2p, 3s2, what was it, 3p3? Or we said phosphorus, I'm tired of writing, neon, 3s2, not neon. No, it was neon. 3p3, right? Okay. I want to now make phosphorus interact with another element. Okay. To do that interaction, what's the first thing that needs to happen? You want to interact with a potential significant other. What's the first thing that needs to happen? Contact. Okay? You need to be close enough to interact with that significant other. If you are not, what happens? Nothing. So we need to bring those 2 things close enough to each other to interact. What's the first thing that's going to interact for phosphorus? The electrons, because they're on the outside of the structure, or the outside of that atom. Which electrons? Well, the outermost electrons, the ones furthest away from the nucleus. Those are going to be the most important ones to interact with something. Okay? So I will call those outermost electrons the valence electrons. Okay? Those valence, okay, it might be nice to get specific. Well, how much is the outermost? The outermost will be the highest energy level. So for phosphorus, what are our highest energy level electrons? 3p3 is a good answer. but it's only half correct. It's all of the third energy level. This says energy level. It says nothing about what orbital they're located in. It's just the energy level. Okay? So the highest energy level will be the 3s and 3p. If I use the shorthand notation, it stands out because those are going to be the highest energy ones. Everything before that is now too far inside. Okay? If I decide not to do that, I just have to remember highest energy level. Okay? Those will be the valence electrons. Those will become super, super important when we talk about bonding. Kind of makes sense? Took about like 6 minutes. Is that clock fast? No? Okay, just check it. Make sense? What do I want to call the other electrons? Not valence. Good definition. I like that one. Okay, come up with a better one. They're the core electrons. They're the ones on the inside. Okay, like the core of our planet. So we've got the core electrons and the valence electrons. We very rarely ever talk about the core electrons because it doesn't matter. Right? Much. Enough. Let's try that. They don't matter enough. The valence electrons are the ones that are going to dictate a lot of our properties. So what you need to be able to go through and do is determine your electron configurations, identify your valence electrons, and you've done orbitals. Okay? So, periodic table, there's our organization. The first two columns are known as our S block, our D block, our P block, and our F block. It's neat, it's organized, it's beautiful. That's why it's there. Okay? That's the periodic table that we deal with. Okay? I don't want to tell you that. Atomic radius. Okay? Remember we said we had a problem with the atomic radius, right? The atomic radius had to do with the size of the atom. What was the thing that was important to dictate the size of the atom? Rhymed with proton. So if it rhymes with proton, it better not be proton, because that would be a horrible rhyme. Starts with E. Electron. There we go. Those rhymed. It doesn't rhyme. Those absolutely rhyme. Electrons. No. And our initial theory was the more electrons we had, the bigger we got. That works great down a column. When we move from lithium to cesium, it gets bigger. Okay? Fantastic. That's awesome. But when we move from lithium to beryllium, we're also increasing in electrons, and yet what happened to the size? It got smaller. So our rule of add more electrons, get bigger is a horrible rule. Okay? It doesn't make sense. But now that we know where electrons exist, we should be able to explain the observation that we're seeing. When we move down a column, why does it get bigger? The nucleus actually has nothing to do with it. Remember, it's the electrons.
More levels, more energy levels.
Where are the electrons going? A higher energy level. Right? That's the rows. So when you go to a higher energy level, of course it's going to get bigger because the electrons are further away from the nucleus, because it's in the next energy level. Okay? It all has to do with where the electron's located. Okay? And in particular, the valence electrons. Why, when we move left to right, do we not see it get bigger? That's a much trickier question. Okay? Well, where's the energy level? Where's that next electron going? It's going to the exact same energy level, because we're in the same row, right? So if it's going to the same energy level, what would we expect to happen to the size of the atom? It stays the same. Okay? That also didn't happen. Damn it. Okay? Why did it shrink? So now we have to consider what else changed. Okay, so there's my nucleus, there's my electron. The next electron comes in at the exact same energy level. The distance doesn't change. And yet, for some reason, it's getting pulled closer. Why would it get pulled closer? something is pulling it closer. What would be the something that attracts electrons? A positively charged thing. What happened when we moved from lithium to beryllium? Yes, we added electrons. What else did we do? We added a proton. What happened to the strength of the nucleus? It became stronger. So while I'm adding an electron at the exact same energy level, I'm making that nucleus stronger, which now means, and the size decreases. Okay. For those of you going like, wow, that's way too hard, I'll never remember that. Memorize the trend, you have your answers. Okay. For those of you who are like, I think I could come up with that, that's good, because I do expect you to be able to explain that as a higher order level question. Right? Do you need an A? Understand that. Do you need a B? Deal with the trend. Do you need a C? Deal with the trend. Okay? Makes sense? Okay. Ionization energy. Okay, everybody gets kind of tripped up on ionization energy. Energy necessary to remove an electron. So I take my atom, my nice little happy neutral atom, and I come along and I remove an electron. Will it want me to remove an electron? Why would that be a bad thing to try and remove an electron from it? What happens to the atom when I remove that electron? It's going to become charged. It's lost something that was neutralizing it. Charge is an inherently bad thing, so that's not good. The next part, not only is it becoming charged, where am I removing that electron to? To nothingness. Okay? If we removed you to nothingness, how happy would you be? If you're an introvert, don't answer that question. Okay? That nothingness makes that electron very, very high energy. Okay? What we're doing, I know, just close your eyes if that bothers you. We're taking an electron from here and we're pulling it all the way out there. We're asking, what is that distance in energy? Okay? Well, if you understand electron configurations, you can predict the ionization energies. Because it's now, where's that electron starting? Where is it ending? I have to buy new AC filters, apparently. It's an alert. Okay. In general, our ionization energy increases as we go from bottom to the top. Well, the bottom has the electrons located where? The highest energy level, which means they are closer or further from the vacuum. Closer, which means the gap between there is very, very tiny. So that's going to be a small energy. At the top of the column, it's as far away from the vacuum as possible. That's a large energy gap. Right? And then in general, it increases left to right. Same concept applies. Think about where the electron is located. How much energy does it need to move? Okay, the thing that tends to freak most people out here is it says in general. Okay? The why in general is that if we look at it, we have exceptions. We'll talk about those exceptions. What is today? Thursday. We'll talk about those exceptions on Tuesday, and then we'll move into Lewis structure. Watch the Lewis structure video. Okay? You will be tested on that content on Thursday. You need to come into class Tuesday ready with questions.